Hello guys and welcome to my blog. In this video I'll try to show you the implementation in MATLAB of the example that was given in the last two tutorial videos that I posted. So I will assume that you guys have seen the videos. The first thing that I will do is show you the graphic that the exercise gives us and explain to you what everything is and what everything represents. After I explain to you what the graphic makes, I will try to explain to you how I did the code and how I implemented the Kalman filters. So I am assuming that you guys have seen the previous two videos, so let's get started. So the first thing I'll do is try to show you the graphics that I obtained from the MATLAB example, and explain to you what that means. As you may recall, the example was of a given ninja that was blindfolded, and this ninja was trying to catch a pigeon. So, however, the ninja, as I said, was blindfolded, so the location that he sees the pigeon, it's not really the correct position of the pigeon. What I mean by this is that there is an error in the measurement of the pigeon location at a given time. So in the x-axis we can see the time. The pigeon flew for 10 seconds, as far as we know, of course, and for a distance of almost 80 meters. And as you can see, there is a great error in the ninja measurements. So this first graphic, this upper graphic, in this upper graphic the ninja will try to locate the pigeon, doing an average of where he thinks that the pigeon is. And as we can see, even though the average is closer to the real path of the pigeon, it is not very accurate. So if the ninja tries to catch or caught the pigeon in this, doing this precursor, he will probably not be able to get it. So in this downer graphic, if you will, the ninja will try to implement a Kalman filter based on his measurements and based on what he thinks that the model of the pigeon flight is. And as we can see, the Kalman filter is pretty much more accurate than the average of the measurements that the ninja made. However, it is not 100% correct as we would expect. As we can see, there are little errors in here, but overall it is not. It is a way better understanding of the pigeon flight, and the error can be despised. Okay, so the conclusion that we get is that using Kalman filter will, knowing the model of the pigeon flight and knowing the measurements of the pigeon of what the ninja sees, using the Kalman filter will give us better results because it will filter all the bad measurements, okay, and will leave us only with the good. Okay, of course, I will repeat this. In this case, we assume that the ninja knows A, what the model of the pigeon flight really is, okay, and B, he is using his measurements to balance it, okay. So this Kalman filter code was implemented by me based on some YouTube videos that I've seen. However, there are probably very packages or very functions where you don't have to do all the math. You just have to define the model matrix, the covariance matrix, etc., etc. However, I chose to do the Kalman filter implementation in order for me to understand better what the Kalman filter is. Okay, so the first thing that I've done was define for how long the pigeon would fly, and how many times, or what was the time interval that the ninja would observe the pigeon. So now here we can see that the ninja looks at the pigeon 10 times per second. Okay. The second thing that we need to do is define the matrix. Okay. These matrices will define the model. A and B will define the model that the ninja is expecting, okay? And the C matrix will define what can be or can't be measured, okay? The next thing that I will do is define what the movement of the pigeon really is. So in this case, I've made a pigeon fly with constant acceleration, okay? The basic Kalman filter can be applied easily with two basic models. One is of constant velocity, that means that acceleration is 0, and the second one is with constant acceleration. Actually, the first one is just a specific case of the second one, but you know where I'm going with this. So this system is linear because the acceleration is constant. So this is the first where the ninja expects the pigeon to be. So the first measurement is where the ninja expects. In this case, he expects that the pigeon is still, velocity is 0, and is in the 0 position, if you will. Okay. The next thing that I've done was define what was the noise that both the pigeon and the ninja suffered. This noise will affect the flight of the pigeon, and this noise will affect the measurements of the pigeon. Okay. Lastly, what I've done was define the covariance matrices in order to later calculate the Kalman filter. So what this first thing does is basically this will create the real path that the pigeon will take. If I go here and I change this from 0.05 for instance 5, I can see that the error of the pigeon flight is way greater than what we were expecting. Okay, so and this is random. Okay, this is not predefined. This is random. What I mean for random is that if I run this over and over and over, I will always get different flights. Okay. So as you can see, okay, so last time, okay, this is good for now. I will put this in where it was before. Okay, blah blah blah. So this will record the pigeon position. Okay. This will plot the pigeon position as well as the ninja measurements. Okay, so in here, what I've done is an average of the ninja measurements, and then I plotted the measures. As you can see in blue, this was the first graphic. Okay, I can show you. I will change this definitely. I hope that this does not go wrong. Let's see. As you can see, the pigeon flight is different from before. Those green dots. Oh yes, if I change this for 100, this is way exaggerated, but you can see that the error of the measurements is way bigger. Okay, let's see what this gives. This does not give anything good, but going back. Okay, this blue line represents the average of the Ninja, of what the Ninja sees. It is not that bad, but it's not that good either. Okay. The next thing that I've done, and this is easier to understand if you do this on paper, but what I've done was implementing the Kalman filter. I implemented the Kalman filter here. As you can see, this is the estimative of the Kalman filter. I store the estimative. Then I predicted the covariance, okay, the error in the measurements, and I stored it as well. Then I calculated the gain. The gain basically tells me how much can I trust in a given measurement, okay. And finally, I updated the provision of the. I updated the position of the pigeon, okay, given the gain, and I stored this. I also plotted, and let's see what I got. This is really the first time that I'm running this at 5 noise in the pigeon. Let's see what I get. Okay, it is not as bad as I expected. Okay, so this is pretty much it. In the next video I will show you a 2D example. That one is more complex, and I hope you guys understood what I've said. Okay, thank you for watching.